Greetings, folks. It's been a while. You've learned how to analyze circuits sort of by the seat of your pants, so to speak. Now you're going to learn how to do it in a more formal way using what are called Kirchoff's laws. That's what this video is about. So this is the same circuit you saw in the seat of the pants video with two exceptions. The first is that I'm not admitting that there are 4 amps of current flowing through R1. And the second is that I will be providing you with a power supply or two in this section here. So here are our power supplies. I'm actually putting 2 in the circuit just to be different. I'm orienting them in different directions just to add the thrill. I'm assuming there's internal resistance to these, which I'm lumping into one little R sub I. We have 1, 2, 3, 4, 5, 6 resistors and 2 meters to deal with. We want to know how much current's being drawn through the battery part of the circuit, which is through this branch here. We'd like to determine what the ammeter is reading, and we'd like to determine what the voltmeter is reading. So as always, we're going to start by redrawing the circuit by getting rid of the meters. And here is that circuit drawn that way. We want to simplify our circuit. We'd like to make it so that the definition of the currents is a little easier to see. So I'm going to go ahead and take this point and connect it there. And I'm going to take this point and connect it there. And there we have the reconnection. We're going to need to define one current for each branch. There are 1, 2, 3, 4 branches. And here are our currents, I1, I2, I3, I4, except if we were clever, we should be able to get it down to only 3 currents. 3 currents would be much nicer to deal with because that would mean we would only have 3 unknowns to hassle with versus 4. How might we do this? By considering what the currents are doing as they enter and exit this node right here. Which brings us to Kirchoff's first law, which is associated with node equations. It essentially says the sum of the currents into a node will equal the sum of the currents out of a node. Written notationally, that relationship looks like this. Sort of schematically, here we have I1 coming in and I3 coming in, so we've listed them here. We have I2, I4, and I5 leaving. We've listed them here. This is a node equation. The point is that the current going through R4 here is going to end up equaling the current coming in, I1, minus the current going through the other 2 branches. What's left over goes through R4. So in a formal sense, what we've already done is to start out writing Kirchoff's laws. We've used the node equation to identify one of our currents. Having done that, having used the node equation to identify our current, now we have to start looking at loop equations. So a loop equation, which is Kirchoff's second law, is essentially the summing of the voltage changes around any closed loop and putting that sum equal to 0. This is the way I would characterize it mathematically. This is the circuit that I'm going to use to animate the idea. So here I've identified the voltage changes across a battery and a couple of resistors. There's actually kind of an important point here. Notice there's a positive sign here and a positive there. There's a negative here and a positive there. There appears to be what looks like an inconsistency. It's identifying a very sort of fundamental point, though, that's important for you to understand. The positive terminal of a battery is positive because of the way the battery is built. Okay, it's inherent. It's an inherent part of the battery. The positive side of a resistor is identified by the direction of the current flow. Current flows from high voltage to low. So if the current's flowing in this direction, this is the high voltage side and this is the low. If the current was flowing in this direction, this would be the high voltage with this the low. In other words, this positive and negative is attached to this resistor, and it's defined by the direction the current is flowing at a particular point in time. In other words, it's specific to the resistor. It's not a global quantity. In any case, In both instances, they are identifying what is the high voltage side of the entity and what is the low voltage side of the entity. So having said that, let's start right here and see what happens as we traverse counterclockwise. As I go through the battery, I go from the low voltage to the high voltage side, which means I execute a voltage increase. As I move along with the current, when I hit the resistor, I'm on the high voltage side of the resistor. I go through the resistor, I have a voltage change of IR, and it's a drop because I'm ending up at a lower voltage than I started. The wire provides no voltage drop, so everything stays the same until I get to the next resistor, another voltage drop. And by the time I get to this point, and this point are essentially the same points as far as voltage goes, because wires essentially take no energy out of the system. Charge carriers traveling from there to there essentially lose no energy. So this point and that point are essentially the same, which means the voltage change between here and here, which are essentially the same points, is going to end up being zero. That's exactly what Kirchoff's law says. The voltage changes around any closed loop have to add to zero. This is the way I would characterize it. This is the way I would write it out algebraically for this particular circuit. So before you can write out loop equations, you have to identify the loops that are available to you. In this particular circuit, there's 6 of them. Here we have one loop, a second loop, a third loop, a fourth loop, a fifth loop, and a sixth loop. We have 3 unknowns. We've already used our node equations to identify the current here, so we're going to need 3 loop equations. I've chosen this loop, and this loop. As a minor side point, you need to have the power supply represented in at least one loop. In this particular case, you have 2 power supplies. They're all in this one branch, which means this loop does the job for you. The second note has to do with the fact that you really only want to have these power sources showing up once in your loop equations. It will just make life easier for you down the line when you're trying to solve your equations. The downside is that for this particular circuit, it means you're going to have to include this branch in one of your loop equations, which is going to be kind of a pain because there's all sorts of stuff involved in it, but that's just life. So beginning with loop 1, I'm going to start at this point right here. I'll call it point A, and I'm going to proceed clockwise. First thing I run into is a battery E2, so I write down E2. I'm going from the lower to the higher voltage side, so it's positive. I run into the resistor. I'm going with the current, so I'm going from higher to lower, which means I'm seeing a voltage drop of I1R1. I'm seeing a voltage drop of I2R2. Again, I'm going with the current. When I get to this battery, I'm going from the high to the low voltage side, so I'm seeing a drop of E1. Going with the current flow through little r sub I, so I'm seeing a voltage drop of minus I1 little r sub I. And that brings me back to point A, which means that's going to all equal to 0. So here is my loop equation for loop 1. And here are all the numbers put in, and here are the numbers rearranged. I've grouped the I1 terms and the I2 terms, and I've taken the constant, the voltage, and I put it on the right-hand side, and I've put the I1 terms here, and the I2 terms here, and the I3 terms here, of which there are none, but I'm putting them in anyway, because it's going to be useful to me down the line when I decide I want to try to solve this thing. So loop 2 is looking like so. I'm going to start at point B, and I'm going to go once again clockwise. And if you just look, you can see I'm going against the current, so it's a voltage increase of I2R2 and a voltage drop of I3R3. And I happen to notice that 40 goes over 123 times, and so I simplified this relationship like so. Here we have loop 3. I'm starting here, and I'm going once again clockwise. And you can follow around You can see as the voltage increase across R3, all the rest are voltage drops. And there's no battery in the circuit. As a minor note, it might have been a temptation to look at this thing and go, oh gee, 10, 5, 5, they're in series, I'll just make it 20, and I'll take 20 times I1 minus I2 minus I3, which is to say all of this. This is a perfectly legitimate thing to do, but it's not recommended. And the reason why is because when you start simplifying stuff straight away with your first relationship, if you happen to screw something up and I can't figure out what you've done, I'm not going to be able to give you partial credit. It's much better to just go ahead and write everything out individually. Once you get it all written out individually, then you can simplify like this. So here are my three equations. This was equation A, equation B, equation C. I have three unknowns. I need to solve these things simultaneously. If you try to do it algebraically, I guess, the easiest way to do this particular combination of equations is to notice that there's an I2 term in each one of these. So I could figure out what I1 was in terms of I2. I could figure out what I3 was in terms of I2. I could get rid of the I1 and the I3 in this relationship and have nothing but I2 terms and solve for I2. Everything I just said is stated here. So here I'm doing this with equation A, and here's my final relationship for I1. And here I'm dealing with equation B, and here's my final relationship for I3. And here I'm taking I1 and I'm substituting in, and I3 and I'm substituting in, and I'm solving and solving, and I'm coming up with I2 equals 0.4 amps. What that means, going back to equation D, is that apparently I1 is 4 amps, which is fortunate because if you remember the seat of the pants problem, I1 was 4 amps. Hee hee. And I3 turns out to be 1.2 amps. We can additionally tell that I4 is going to end up equaling 2.4 amps. So now we can go back to the problem's original questions. The first question was how much current was there in the section or the branch in which the power supplies existed. That was I1, 4 amps. Second question was what did the ammeter read? You can see if I1 is 4 amps and I2 is what, 0.4 amps, what is left over is going to go this way, which is apparently 3.6 amps. That's what the ammeter would read. The voltmeter is just the voltage across R2, that is I2R2, apparently it's 48 volts. So I've gone ahead and solved this problem for you, and you've had a chance to see it done, and it probably looked pretty easy the way I did it, except a lot of people don't like algebra very much, and the question is there an easy way or an easier way to do this that will always work? And to that there is good news and bad news. The good news is that the answer is yes, there is an easier way to do it. The bad news is that it requires you to deal with a matrix. So I'm going to talk about this in class, but I'm going to show you very quickly how it works. So here are your three equations. You're going to take the I1 coefficients and you're going to list them in this matrix. I2 coefficients, list them. I3 coefficients, list them. Constants, list them. Okay, kindly notice this matrix is called the determinant. If I want to know what the solution to I1 is, it's equal to the ratio of the evaluation of two matrices. The bottom matrix is the evaluation of the determinant. So it's just this thing brought down. I'll talk about how to evaluate it in a second. The top matrix is the determinant with one alteration, the alteration being that the column that's associated with the variable you're solving for is substituted out with the constants. So this is the I1 column. The constants have been placed in there. 120, 320 is the same. 0, minus 1, and 60 is the same. It's the determinant with the column associated with the variable you're solving for being swapped out for the constants. So to evaluate a matrix, I always take the first and the second column and I reproduce it over here. You'll see why in a second. The process is to take this variable, 280, and multiply it by the evaluation of this little 2 by 2 matrix. And the way you do that is you take the upper left times the bottom right, which is 3 times 60, minus the upper right times the bottom left, minus 1 times 20. So it's this times this minus this times this. To that, you want to add, you go over 120 times the evaluation of this little 2 by 2 matrix. Except you'll notice that there's zeros in these two, which means this quantity is going to go to 0, which is nice. And in fact, this quantity times that minus that times that is also going to give you 0, which is nice. Minor point. Notice that we had one loop in which there were voltages and two loops in which the voltage was 0. The reason why we wanted to do that, if you can do that, is that you will get this nice situation where the numerator only has one quantity that's non-zero in it. All the rest have a 0 times whatever and a 0 times whatever. This is why we chose to take the outside loop, even though it had more resistors and more currents in it to hassle with, over having a second loop in which the battery voltages were available. Anyway, evaluating the bottom matrix in the same way gives you this. Doing the math gives you like so, and lo and behold, I1 ends up being 4 amps. The reason why this approach is easy and better, as far as I can see, is that it's just rote. It's not algebra. You don't have to be clever. All you have to do is just to put the coefficients of the current variables into a matrix and then know how to manipulate a matrix. And manipulating and evaluating a matrix is really easy. It's just this times that minus that times that, plus this times that minus that times that, plus this times that minus that times that. That's all there is to it. Any idiot can do it. What's more, if you're dealing with numbers, you can literally do it in your head. So you've got 248 times 3 times 60 is 180 minus a minus 20, which is plus 20. So 180 and 20 is 200. You just basically did it. You don't have to write out all of the individual stuff. Then you go to here and you say 120 times, oh, that's 0, don't have to worry about it. 0 times, oh, don't have to worry about it. There is your numerator right there. Boom, you did it in about 15 seconds. Same thing with the denominator. 50 times 3 times 60 is 180 minus 20 is plus, so you got 200 times 50. 120 times minus 1 times minus 20 is plus 20. Zeros is plus 20. You're done with that piece. Then 0 times, whoops, you're done. Okay, you could literally do it in your head in just a few moments, at least getting to this point. There is a second way to solve for these 3 equations, or if that meant any number of equations, with a determinant matrix. And that is the following with a calculator. You put the matrix into your calculator. You determine the inverse matrix. You multiply the inverse matrix by that 1 by 3 matrix that held the voltage constants. And it will give you a 1 by 3 matrix that will essentially give you the solution to the unknowns, which in this case will be the 3 currents. In an algebraic sense, inverse matrix times the constants equaling the currents. For our problem, here is the matrix, here's the inverse matrix, here are the voltage constants, here are the currents. Anyway, this is not something you necessarily have to use on a test. It just, if you happen to be good with a TI or any calculator for that matter, it's just an even faster way to go ahead and get solutions simultaneously with equations. Anyway, that's it.